Inside the human body lies a remarkable communication system that transforms thought into motion at astonishing speeds. Elite sprinters possess neural pathways that operate with extraordinary efficiency, creating a brain-to-muscle connection that separates world-class athletes from everyone else. Sprint performance depends critically on how effectively the brain communicates with muscles. Your nervous system fires signals at up to 120 Hz in champion sprinters, coordinating hundreds of muscle fibers every 8 milliseconds. These signals dictate when muscles contract, how forcefully, and in what precise sequence. The speed and coordination of these signals determine how effectively a sprinter can utilize their physical attributes. The difference between average individuals and elite athletes in this neural communication is striking. Research by physiologist Peter Wine found that elite sprinters' nervous systems can activate approximately 90% of their muscle fibers simultaneously, while average people typically recruit only 60 to 70%. This means two people might have identical muscle fiber composition, but the elite athlete can access significantly more of their muscles' potential power with each contraction. This neural advantage isn't entirely innate. It develops through years of specialized training that strengthens the connection between motor neurons and muscle fibers. Each time a sprinter practices an explosive start or maximum velocity running, they're reinforcing the neural pathways that control those muscles. Over time, these pathways become more efficient, allowing faster signal transmission and more complete muscle fiber recruitment. The neural advantage appears from the very first moment of a race. Reaction time at the starting block, the interval between the starter's gun and the first detectable movement, represents the first test of neural efficiency. In his record-breaking race, Bolt's reaction time was measured at 0.155 seconds, remarkably fast for someone of his height. This fraction of a second represents the time needed for sound to reach his ears, for his brain to process that sound, and for signals to travel to his muscles initiating movement. Even this brief interval reveals extraordinary neural efficiency. Throughout the race, the brain must perfectly coordinate the firing of hundreds of muscles while making split-second adjustments based on feedback. Consider what this entails. With each stride, the brain processes information about body position, ground contact forces, momentum, and balance. It then adjusts the precise timing and force of hundreds of muscle contractions to maintain optimal form. All of this happens without conscious thought, managed by neural circuits that have been refined through thousands of hours of practice. The complexity of this neural choreography becomes apparent when you consider the speed at which it happens. At top velocity, a sprinter's foot contacts the ground for approximately 0.1 seconds. Within this brief contact, the brain must coordinate the proper sequence of muscle activations to absorb impact, generate force, and prepare for the next stride. Any timing error of even a few milliseconds can disrupt the entire sequence, wasting energy and slowing the sprinter. Elite sprinters show enhanced neural drive that allows them to reach peak force generation in about 70 milliseconds compared to 120 plus milliseconds in non-athletes. This faster rate of force development means they can generate maximum power much more quickly with each stride. The difference might seem small, but in a race where hundreds of seconds matter, this neural advantage becomes crucial. It allows elite sprinters to apply more force to the track with each step, resulting in greater acceleration and higher top speeds. Neural efficiency also explains why some sprinters maintain better form as fatigue sets in. As a race progresses, muscles begin to fatigue, making them less responsive to neural signals. Sprinters with superior neural efficiency can maintain muscle recruitment patterns more effectively even as fatigue accumulates. This allows them to maintain proper form longer, reducing the inevitable deceleration in the final phase of the race. Could future training methods enhance this neural connection beyond current human limits? This question fascinates sports scientists. Traditional training methods already target neural efficiency through exercise like plyometrics and resisted sprints. Plyometric training, which involves explosive jumping movements, has proven particularly effective at enhancing neural drive by training the nervous system to activate more motor units more quickly. Reflex training, which focuses on improving the speed of involuntary muscle responses, also shows promise for developing faster reaction times and more efficient movement patterns. What makes neural efficiency particularly interesting is that it represents one of the few areas where training can still push human performance closer to theoretical limits. While factors like muscle fiber composition are largely determined by genetics, neural efficiency remains highly trainable throughout an athlete's career. Even athletes with less favorable genetic attributes can significantly improve performance by optimizing their neural systems. The importance of neural efficiency extends beyond the individual muscles to the coordination between muscle groups. Elite sprinters display superior intermuscular coordination, the synchronized activation of multiple muscle groups. This coordination ensures that antagonistic muscles, those working in opposition to each other, don't counteract each other's force. When a sprinter extends their knee explosively, for example, the hamstring muscles must properly relax to allow full extension. Any coordination error creates internal resistance that slows the movement. Understanding this neural component of sprinting helps explain why raw strength doesn't always translate to speed. Many athletes can generate tremendous force in isolated movements like squats or leg presses, but lack the neural efficiency to coordinate these forces during high-speed running. The ability to apply force at high velocities, what scientists call rate coding, matters more for sprinting than absolute strength.